Hello everyone and welcome to today's Chemistry Daily Booster. This is paper 2, number 3 in our series. This is going to have some of the advanced information listed topics for both the higher and foundation chemistry students today. What we're going to do first of all then is focus on the transition metals. Now hopefully we remember that when we look at our periodic table, and we've got this lovely little layout of it like so, the transition metals are this block in the middle here, okay? Now they're found between group 2 here and group 3 over here. So the transition metals are, first of all metals. Again, the name kind of gives it away there, which means they've got typical properties of a metal. They're shiny when freshly cut, good conductor of electricity, they're strong, they're malleable, all typical metal properties. Because we've had to look at one other group that contains metals, group 1, the alkali metals, we need to be able to compare group 1 and our transition metals. So in terms of what we see, the transition metals are stronger than group 1, they're harder than group 1, they have a higher density and a higher melting point. So I'd make sure that you can name at least 2 of those properties. Great if you can learn all 4, if not, hit a minimum of 2, because then you've got 2 points you can use as a comparison. As far as their chemical properties go then, our transition metals react really slowly if they react at all. So a good example of one of these slow reacting metals in our transition metal category is iron. Now iron will react with oxygen and water to make hydrated iron 3 oxide, more commonly known as rust. Hopefully we do know rusting is a slow old process. It's not like if you leave a bit of iron outside overnight, gone, it's just a pile of rust by the morning. It takes a while. So it's a slow reaction. If we consider some of our other transition metals, something like platinum for example, does not react with water or oxygen at all. Hence why platinum is great to use in things like jewellery, because it's not going to react with the oxygen or the water that you come into contact with all the time while wearing that jewellery. One of the tricky points, if you like, about the transition metals is they can actually form more than one type of ion. So where we've previously been able to learn that group 1 make +1 ions, group 2 +2, group 6 -2, group 7 -1, there's no hard and fast rule for our transition metals because they have options. Instead, the way that we know the charge on that metal ion is by looking at the Roman numeral that its name has. So in this case, we've got the Roman numeral for 3 in brackets. So that means we've got iron 3+ ions. Because there's the 3 in brackets, 3+. They're metals, they will always be positive. If it was only a 2, 2+. If it was a 1, 1+. 4, 4+. You get the idea. When we consider the kind of compounds that our transition metals make, they make coloured ionic compounds. Whereas if we compare to our alkali metals and their compounds, they tend to be white or colourless. So the transition metals are way prettier. They come in purples, greens, blues, greens. Lovely. Whereas the alkali metals, white or colourless. They're dull. So remember, alkali metals, white or colourless compounds, transition metals, a range of coloured ones. In terms of some of our uses of the transition metals, they are pretty good catalysts. Now, catalysts, remember, are some kind of chemical that's going to speed up a chemical reaction without being used up itself. They can ask us questions on catalysts on paper 2 in a couple of different sections. Key thing is we're looking for something that's increasing the rate of the reaction, but the mass is going to remain the same start to finish, the colour remains the same from start to finish. Literally the only thing that's going to change is the rate of the reaction. It's going to get faster. So just remember that little point about catalysts, because they can ask it, giving you a table with different masses at the start, masses at the end, colour at the beginning, colour at the end, and the rate of reaction in the table, and ask you to pick the catalyst. Examples of where we also use our transition metals is in our cars, in the catalytic converter. Now, catalytic converters in cars use some of these quite expensive metals, platinum, rhodium, palladium, and the reason that they are present and the reason these catalytic converters exist is because they're going to convert some of the harmful exhaust gases that cars produce as a result of that internal combustion engine into less harmful ones. So this is kind of one of those environmentally friendly techniques that we now have. We do need to know about the reactions of metals as well here. So hopefully we do remember all metals form positive ions, and the more easily that ion is formed, the more reactive the metal is. There are a few reactions we really need to know. First of all, a metal and water. What we're going to find is a metal will react with water if it's more reactive than hydrogen. Same rule here for metals reacting with acids. If the metal is more reactive than hydrogen, a reaction takes place. If it's not, it doesn't. So metal plus water makes metal hydroxide and hydrogen. That should look familiar because we did it in our group 1 lesson. So metal and water makes metal hydroxide and hydrogen, same as our alkali metals. The second one, metal plus acid, makes a salt and hydrogen. Again, we have encountered this previously. Remember when we say salt, we need to be able to write the name of the salt. And to do that, it's always the name of the metal first of all, and then the second word is based on our acid. So if it's hydrochloric acid, chloride, sulfuric acid, sulfate, nitric acid, nitrate, phosphoric acid, phosphate. So that's how we get the name of our salt. Because we're saying hydrogen is made, they could ask you how we test for hydrogen. Lit splint makes a squeaky pop is the answer there. We can also see one of these links into working out rates of reaction. So this could be maths based, could be practical based. In any reaction where we make a gas, if we've got a way to measure the volume of gas made in a given time, we can work out the rate of reaction. Because quite simply, it's just going to be volume divided by the time to give you the rate there. If we're making more gas, then we have a faster rate. There's a few ways that we can measure this. Counting bubbles, remember, terrible, because the bubbles are all different volumes and you can miss them. We can use the inverted measuring cylinder. Again, there's the risk that you could have a little bubble of air in there rather than having it completely full of water at the start. Or the best one, this is our improvement to counting bubbles or upturned measuring cylinders, use a gas syringe. Catches all the gas, you just read off the volume. Now, in the advanced information, we need to know about reactions in displacement reactions. Here is another example. We've done the halogen displacement reactions. These are the metal displacement reactions. So either could come up under that heading there. In a displacement reaction, a more reactive metal displaces the less reactive metal. Similar to what we said about halogens, the more reactive halogen displaces the less reactive halogen. So whatever is more reactive is going to displace the less reactive one. They're not going to expect you to memorize the reactivity series. They will give you a reactivity series. So all you need to do is looking at the information that was in the question, work out, is that going to displace or not? i.e., is the metal on its own more reactive than the one in the solution? If the answer is yes, it will displace. So here's our example. We've got copper and it's going to react with silver nitrate. So because copper is more reactive than silver, then we're going to make copper nitrate and silver. So all that's really happened there is our copper has taken the place of the silver. So you can see all that we've done is just swap copper and silver around. Now, what we do need to bear in mind are some charges, okay? In the question, they will tell you a little bit more. Obviously, I've not given you the full written question here, but they would tell you that we've got something along the lines of copper 2 nitrates being formed. Now, because we've got the 2 in brackets there, the Roman numeral, that means that has a 2+ charge on it. Hopefully we know from paper 1 that nitrate ion is a single negative charge. Therefore, if we've got 2 positives, 1 negative, when they join together, we've got to have 2 nitrates for each copper to cancel out the charges. If we look at the half equations then, we start off with copper on its own. We know we're going to form copper ions, which we've just looked at here. They're going to be Cu2+. Incidentally, if they just give you this, again, if you know that nitrate is NO3-, and we can see that there's 2 of them here, that tells us that our copper must be Cu2+. So that helps us out with the half equation here. And then, because obviously we're going from copper atoms to copper 2+ ions, we also have to have 2 electrons there. So what's happening? Our copper atoms are losing electrons, therefore it is oxidation. Considering what happens to our silver, Ag, in that case, because obviously there's a single silver joined to a single nitrate there, that means it's Ag+, and we're going to make just silver atoms. So in order to get rid of that positive charge, they've got to gain 1 electron to make our silver atoms. Gain of electrons, it's a reduction. Because these 2 are happening at the same time, it is of course a redox. In terms of some useful patterns to remember then, group 0, noble gases, don't react. Group 1 and 2 become more reactive the further down the group you go. Group 7 become less reactive the further down the group you go. Groups 1 and 2 are more reactive than our transition metals. Metals may form ionic compounds with reactive non-metals, because remember, ionic compound is metal and non-metal. And reactive non-metals form covalent compounds with each other, because a covalent compound is non-metals joined to non-metals. We're not going to have a daily booster for chemistry tomorrow because we are going to be doing a live stream instead. So don't forget to join us at 6 PM for the live stream on the channel for the chemistry paper 1, where we're going to have a run through of absolutely everything on the potential questions for C1, C2 and C3 on the OCR Gateway course. We should be able to do that in about an hour and a half-ish, might go a smidge over, hopefully not, but do join us for that. Our chemistry daily boosters will then be back after the chemistry exam has been sat. Don't forget, if there are some bits on this particular topic that you want to go over in a bit more detail, you have the videos on the main channel, you've got your revision guides, and do take a look at some of those past papers before you sit this exam as well. Look forward to seeing you in the live stream, and don't forget to rejoin us when we start up with our boosters again.